Hello everyone, and welcome to Project 23076. My name is Chris Hedgecoke, and I am the team lead of the Perio DX team and a member of the Biomedical Engineering program. Our team consists of my fellow biomedical engineers, Christian and Evelson and Abby Prescott, as well as members of the Electrical and Computer Engineering program, Joy New and Cameron Matsumoto. Our project story begins with the leading cause of death in the United States for the past 75 years, heart disease, as well as one of its most contributing factors, chronic kidney disease. As millions of people around the world are affected by these diseases every year, early detection becomes a crucial component in potential survival for these patients. Currently, in-lab blood testing remains as the exclusive method of detection for these diseases, which are generally signaled by an elevation in inflammation biomarkers found in a patient's blood sample. However, the extreme cost, invasiveness, and wait time for results of these blood tests highlight the necessity of a point-of-care testing device that will allow for early detection of these elevated biomarkers and ultimately save lives.
To combat this issue, our team has developed a paper microfluidic system in conjunction with a companion smartphone application that is capable of detecting two of the most commonly elevated biomarkers in patients with heart and kidney disease, MMP9 and IL-6. However, to improve on the cost, invasiveness, and wait time issues, our test utilizes a fluid found in the periodontal pocket, which is found between the tooth and gum line, called gingival crevicular fluid, or GCF, which has been found to contain the same inflammatory biomarkers, MMP9, IL-6, that are found in blood samples of heart and kidney disease patients.
To capture and test for these biomarkers, our team has designed a lateral flow assay, or LFA system, which can be seen in the following diagram. The mechanism behind biomarker detection is akin to that of a COVID or pregnancy test, where a GCF sample, theoretically containing MMP9 and IL-6, is captured at the periodontal pocket via the cellulose fiber sample pad. Capillary action will then carry this sample to the cellulose fiber conjugate pad, which has been preloaded with gold nanoparticle conjugated antibodies that correspond to either MMP9 or IL-6 depending on the test strip being used. Here, primary binding will occur between the biomarker and tagged antibody, creating a tagged antibody-antigen complex that will continue to move through the strip. This complex will then reach the test line located on a nitrocellulose membrane shown in gray, which has also been preloaded with generic anti-MMP9 or anti-IL-6 antibodies. Here, secondary binding will occur between the gold nanoparticle tagged complex and these antibodies, inciting a color change on the test line whose intensity is indicative of the relative amount of biomarker present in the original sample.
Once the biomarker has been detected by the LFA strip, the relative amount of antigen found in the sample is read out by our companion app. A description of this process can be outlined by the system block diagram shown here. Test analysis begins once the user opens the application. They will log in or create an account and be shown the instructions on how to collect the sample and analyze the test. After the test has been completed, the user will capture an image of the test line. The app will then process the image using the OpenCV library provided by Python. This is when the application will analyze the test line to determine the antigen intensity. The color analysis algorithm will then target the RGB, or red, green, and blue, intensity values for the test line. The green intensity of the test line is the point of interest because lighter shades of red will contain more green intensity and darker shades of red will contain less green intensity. Thresholds for this green intensity have been calibrated with LFA strips with different concentrations of each biomarker to determine if there's a low, medium, or high risk. Once the image has finished processing, the result of the test is encrypted and uploaded to a secure database. The user will then be automatically directed to a page where they can view their test results. The results are displayed in a table that show the date of the test, the antigen being tested, and the associated risk factor.
The following system requirements have been deemed necessary for our LFA system to be successful. The device shall be able to detect IL-6 and MMP9 levels of at least 35 picograms per milliliter and 376.6 nanograms per milliliter, respectively. These distinct levels were determined as our minimal threshold as they are the clinical determination of elevated levels in relation to heart and kidney disease. Additionally, the device shall utilize gold nanoparticle conjugated antibodies to incite a color change, shall be loaded with the proper levels of these antibodies, and shall utilize capillary action to create an autonomous flow of sample.
To accomplish these system requirements, the LFA strips were manufactured in the following fashion, which begins with the addition of 10 microliters of phosphate buffered saline to the cellulose fiber sample pad, as shown here, to help stabilize the sample once it is collected. Immediately following this, 10 microliters of gold conjugated antibodies that correspond to either MMP9 or IL-6, depending on the test, is deposited onto the cellulose fiber conjugate pad, where primary binding will occur. Finally, the test line of the LFA is prepared by adding 4 microliters of non-conjugated antibodies to the nitrocellulose membrane, approximately 1 centimeter away from the end of the conjugate pad, and that process can be shown playing out here. Once the appropriate biologics have been added, the sample pad, conjugate pad, and NC membrane of the device will all be placed into a 37 degrees Celsius oven, where the sample pad and NC membrane will stay for 30 minutes, while the conjugate pad will stay for an entire hour. After the components are retrieved from the oven, final assembly can occur by first placing the conjugate pad onto the backing card, which will be followed by the sample pad, which will overlap with the conjugate pad, as shown here.
System requirements have been deemed necessary for our companion application to be successful. A simple user interface shall be created utilizing the Python framework and the Android platform. In terms of accuracy and usability, the application's readout of relative amounts of biomarkers present in the sample shall be accurate no less than 95% of the time.
To begin complete system testing, the sample pad of the LFA device was first inserted into a sample of mock GCF that simulates a patient's periodontal pocket and contains levels of MMP9 and IL-6 deemed in the system requirements shown previously. As can be seen in the time lapse, capillary action properly carries the sample through the necessary LFA components and incites a color change which can be seen immediately following the conjugate pad on the bottom portion of the device. Immediately following this color change, our application will capture a photograph of the test line, which is then analyzed and a readout of relative biomarker amount will be provided. This process can be seen taking place for tests loaded with a high and medium amount of antigen, which the application was accurately and correctly able to identify.
The following verification table was produced following several rounds of testing similar to that just shown. As can be seen, our system was successfully able to detect both MMP9 and IL-6 at clinically relevant levels, as well as function autonomously. Accuracy percentages for the results of 95% were met for both the application and the LFA system. Finally, the total cost of manufacturing was found to be about $30 per test, leaving us a margin of $20.
Throughout this process, some unforeseen problems occurred. We learned to deal with these by contacting experts in the field of biomedical and software engineering. We also learned the importance of organization and well-written documentation.
Future directions of this device could include applying the same technology to other biomarkers found in heart and kidney disease patients for a better approach.
Future iterations of this app can implement an image recognition algorithm to automatically detect the test line and connect to the electronic health record to allow physicians to remotely view all the patient information.
Thank you very much for your time, and once again we'd like to thank our wonderful sponsor, Dr. Marvin Slepian, as well as our project mentor, Don McDonald.